Good evening. Today we will see the solution of the questions of day 3 part 1. In day 3 part 1 we have columns, and day 3 part 2 we have actually combined loading or combined stresses, we can say. So now determine the ratio of strength of a solid steel column to that of hollow column of the same material and having the same cross-sectional area. The internal diameter of the hollow column is half of its external diameter. Both the columns are of same length and same end conditions. So now we will first see given data. We have area of solid equal to area of hollow. L we have same, and therefore end conditions we have same, and therefore we have L effective same. Now formula, if you will see, for PE, pi square EI upon L effective square. Now pi square same, E same, L effective square. So what we will get? PE of solid column equal to I of solid column, PE of hollow column, that is equal to I of hollow column. So we have to find I of solid column and I of hollow column. Now for that we require a diameter. So we have ds will be the diameter of solid column and capital D and small d, these are internal and external diameter of hollow column. Now area same, so we will have pi by 4 ds square, that is equal to, now small d we have 0.5 capital D. Therefore we have pi by 4 d square minus d square. Now this pi by 4 gets cancelled. So we have ds square, that is equal to d square minus 0.5 d whole square. If we will take d square common from this, so we have in bracket 1 minus 0.5 square. And from this we will get ds, that is equal to 1 minus 0.5 square, and the root of this we have 0.87 d. Now we have comparison PE solid upon PE hollow, and that is equal to I of solid upon I of hollow. Then we have I of solid pi by 64 ds to the power 4 divided by pi by 64 d to the power 4 minus d to the power 4. Now this gets cancelled, and ds we have 0.87 d. So we have PES upon PEH, and that is equal to 0.87 d to the power 4 divided by d to the power 4 minus 0.5 d to the power 4. And therefore equal to, we have 0.87 to the power 4 d to the power 4 divided by, we can take d to the power 4 common, so 1 minus 0.5 to the power 4. So this D4 gets cancelled and we have PES upon PEH, and that is equal to 0.87 to the power 4 divided by 1 minus 0.5 to the power 4. And if we will solve this, then we have this is equal to 0.87 to the power 4 divided by 1 minus 0.5 to the 4 comes 0.61. And therefore we have PES upon PEH, and that is equal to 0.61. So this is first problem. Now we will switch over to the second. Compare the crippling loads given by Rankines and Ehlers for the tubular strut 3.5 meter long. Outer diameter 40, internal 3 by 4th of outer diameter. Columns are pinned at both ends. Assume FY 350. Does the Ehlers formula cease to apply? And then we have to solve this. So now E is not given. So if not given, we have to consider value of E, that is always 200 into or 200 GPa. Now we will start with. So we have given capital D 40 millimeter, small d 3/4 of 40, so 30 millimeters. Now we will find properties. A we have pi by 4 into d square minus d square. And from this we will get value of A, that is equal to 549.78 millimeters square. Then we have I equal to pi by 64 d to the power 4. In an exam, you have to write formula. So now we have solved so many problems, so I am not writing over here. D to the power 4, and we have this value 1.75 into 10 raised to 6 millimeter to the power 4. So now we have A, and now we can find the value of PE. So we have simply PE is equal to pi square E I. So always keep in mind minimum upon L effective square. Now we have given columns are pinned at both ends. So L equal to L effective, and that is equal to 3500 millimeters. And from this we will get PE is equal to pi square E, we have 200 into 10 raised to 3. I we have same along both the axes. 1.75 into 10 raised to 6 upon L effective square, we have 3500 square. And from this we will get value of P. So that is equal to pi square into 200 to the power 3 into 1.75 to the power 6. 281.99. So we can say 282 into 10 raised to 3 Newton. So PE is equal to 282 kilonewtons. Then we will go to PR. So we have PR, that is equal to sigma C into A divided by 1 plus A into lambda square. Now A we have sigma C divided by pi square E. Sigma C is given Fy 350 divided by pi square, and E we have 200 into 10 raised to 3. I already mentioned A we have to find always 1 upon, so we have shift pi square E divided by 350 is 5.64, or we can write 5639.78. So we have 5639.78. Then we have to find lambda. Lambda we have L effective upon R minimum. So L effective we have 3500. R minimum we have root of I minimum by A. I minimum we have root of, we have same already I mentioned about both axes, 1.75 into 10 raised to 6, and area we have 549.78. We have R minimum, that is equal to 56.42 millimeters. 56.42, sorry. So we have 56.42. And from this we will get lambda is equal to 3500 divided by 56.42, and lambda value we will have 62.03. Now substitute in PR. So we have PR is equal to sigma C is Fy 3550 into area is 549.78 divided by 1 plus A we have 1 upon 5639.78 into lambda square 62.03 whole square. And from this we will get value of PR 114.38 into 10 raised to 3 newtons. And we will get PR equal to 114.38 kilonewtons. And now if you compare this, so we have PE upon PR, and that is equal to 282 upon 114.38, and we have this value equal to 282 divided by 114.38, 2.47. Second part we have below what length of strut does the Euler's formula cease to apply. So already we have seen, we have formula that is lambda greater than or equal to root of pi square E upon Fy. Now lambda greater than or equal to root of pi square into 200 into 10 raised to 3, and Fy we have 350, which will give us value lambda should be greater than or equal to 75.1. Now lambda we have L effective upon R minimum, and that should be greater than or equal to, R minimum greater than or equal to 75.1, and therefore L effective should be greater than or equal to 75.1 into, we have R minimum 56.42, and from this we will get L effective should be greater than or equal to 4237.14, and then we have L effective that is equal to L, and therefore it should, if it is less than this, then we have ceased to apply. So L effective should be greater than or equal to, sorry, L greater than or equal to 4237.14 millimeters. So below this, your formula, below this actually, we have PR we are not using. L should be greater than, for this to apply PE, sorry. For PE, L should be greater than 4237.14 mm. So this was second problem. Now we will go to the third. The cross section of a column is rectangular in section having outer dimension 200 by 120. So we will go with 200 by 120. So we have this as 200 and then we have 120 and thickness 10. So we have given thickness 10, means we have to subtract thickness from both sides. So if we will subtract 20, this 120 becomes 100 and 200 becomes 180. It is fixed at both ends. If the buckling load given by Rankine formula is 900, find the actual length of column. Assume crushing stress. So this is given sigma C or Fy 300 MPa. Now we have to solve this. Now we will go for PR formula. So what is formula of PR? Sigma C into A upon 1 plus A lambda square. Actually, lambda is also given. Sorry, A is given 1 upon 7500. Lambda we have root of under root of I minimum by A. Now keep in mind, we have this will be x-x axis and we have this will be y-y axis. So we have to find I minimum. So first we will find Ix. So we have Ix equal to BD cube by 12. So 200 into 120 cube by 12 minus we have 180 into 100 cube by 12. And from this, we will get value of Ix 13.8 into 10 raised to 6 millimeter to the power 4. Now, if we will find Iyy, then we have this will be 120 into 200 cube by 12 minus 100 into 180 cube by 12. And we will get Iyy that is equal to 120 into 200 cube by 12 minus 100 into 80 cube by 12. And we have this value 75.73 into 10 raised to 6 millimeter to the power 4, which is greater than Ixx. And therefore, I minimum is Ixx. And then we have lambda is I minimum upon A. We have to find A, that is equal to 200 into 120 minus 100 into 180. And we have this value 6000 millimeter square. From this we will get, that is, this is not lambda, this is actually R minimum. And lambda we have L by R. L effective upon R minimum. So we have R minimum, that is equal to under root of I minimum by A. I minimum is 13.8 into 10 raised to 6 divided by 6000. And we will get R minimum 47.96 millimeters. So 13.8 to the power 6 divided by 6000, root of answer, yes. So now we will put values in the formula. So we have 900 into 10 raised to 3, which is PR given. Sigma C is 300. 300 into area is 6,000. So we have 300 into 6,000 divided by 1 plus 1 upon 7500 lambda square. So from this, if we will take 1 plus lambda square upon 7500 on this side, which is equal to 300 into 6,000 divided by 900 into 10 raised to 3. So this 10 raised to 3 gets cancelled. This 2 gets cancelled. So 3 3s are 9 and 3's 2's are 6 is 2. Therefore, lambda square upon 7500 equal to 2 minus 1 equal to 1. And therefore, lambda square equal to 7500. And from this we will get, therefore, lambda equal to root of 7500, 86.6. And we have lambda equal to L effective upon R minimum. Now we have lambda is therefore 86.6 equal to L effective upon R minimum is 47.96. And from this we will get L effective equal to 86.6 into 47.96, 4153.34 millimeters. We are interested actual length. So we have L effective equal to L by 2 because we have both end fixed. And L effective we have 4153.34 equal to L by 2. And therefore L, which is actual length, and that is equal to 8306.68 millimeters. Formulas we have same, only substitutions we are going to different. So this is about part 1. Next video we will see part 2. So thank you.